Now let's look at the advantages and the limitations of start and time modeling. It is a rational method of design because it's not a very empirical approach. Well, because the process is very simple. If you think in generally that we are thinking that the load will be carried by a system which is made of what? Made of the compressive fields and tensile fields, and they are connected at the interconnected nodes. So the tension fields are represented or called ties, and the compressive fields are called struts. Okay, so that way it's a very rational approach. Now the strut and tie model in a structural concrete member adapt to its geometry, loading, and support condition. Very important. We'll come into the geometry also. One of the important thing here is it is a geometry which comes into picture. We'll see later on how. A strut and tie model developed for a specific member cannot be used for the design for other members. It may not be unique either. And delete that. So it may not be unique means if you have different designers, they may come up with a different strut and tie model. So this is the thing. That means you can have slightly different designs even for a same structure, which is fine. Different models must be developed for multiple load cases and check. This is very important. For multiple load cases, if you have different models, then you can check them. Some general guidelines from clause 7.1. Now, the standard clearly explains all these clauses. So if you look at 3600/2018, section 7, there is not much change. I've seen there's no change from 2009. So the section 7 of the standard, it talks about start and time modeling. So it's worth looking into the standard when you are studying this model, and also you can feel free to annotate it. This is important. Now at a node of RC members, the angle between the axis of the inclined struts and the tie should not be less than 30 degrees. Remember, we are talking about 45 degrees. Now here they have reduced this one as 30 degrees, but still, you know, people many times prefer 40 degrees or higher because that is much better approach. But yes, what the standard is saying, if you provide up to 30 degrees, it will be acceptable. So it's fine. Pre-stressed concrete beams can be analyzed by considering the pre-stressing forces as external loads. Ties shall be permitted to cross struts. Put a full stop. Struts shall cross or intersect only at nodes. Okay. Now these are some general guidelines. Now next step is to design the struts, ties, and nodal zones. Now I will read one or two things from the standard because that clearly tells you or summarize some of the things, and then we'll move on. So if you look at section 7, it talks about the general explanation about the strut and tie model. It clearly says that strut and tie models shall satisfy the following requirements. Some of the requirements you have already seen here. Now, some of the general ones are loads shall be applied at nodes. You can see this one just like truss. The struts and ties shall be subjected only to the axial force, which are very clear because we are talking about truss analogy. And the model shall provide load paths to carry the loads and other actions to the supports or into adjacent regions. So you can see the model will provide the load paths. The model shall be in equilibrium with the applied loads and the reactions. Again, we are talking about the static equilibrium. In determining the geometry of the model, the dimensions of struts, ties, and nodal zones shall be taken into account. So this is very important when we are creating the dimensions of the member. So these are some general guidelines. These are very important guidelines. Now let's move on. So let's assume now that we have the strut and tie model, because we have seen there are 3 different approaches we can use to develop a strut and tie model. Imagine we have the strut and tie model here. Now this is very important. If you don't have the model, then you cannot proceed further. So once we have obtained the model, then we will design the components. Now what we have to satisfy, you have to satisfy the model geometry, very important. The serviceability, we already know what the serviceability is. and the ultimate limit state strength requirements. So apart from this serviceability and ultimate limit state, which you are already familiar with, we are also talking about the geometry here. This is very important, geometry. Now let's look at one by one how to, what are these members. First, we'll start with strut. The compressive stress fields are idealized as struts. Struts are basically just like columns, but shorter version of column you can think of. Basic compressive fields can be prismatic. That means uniform compressive field. You can see this is uniform. That's called prismatic. Then you can have non-uniform types like the fan or bottle type. This is fan, which still you can consider that there is a divergence there, but that divergence is not that significant as compared to the bottle. Because bottle, if you look at it, it is just like you have a water channel and then you are suddenly expanding the water channel. Yeah, it is the same thing here. That's why this is called highly divergent stress field. So this is the bottle. Highly divergent stress field bottle type. And this is your fan. So what happens is when you get suddenly expanded, that means you have a larger area to carry the same load. What happens? As a result, there will be some cracks, and there you can have bursting forces acting. No, we'll come into that. Sorry, we'll come into that when you look into the bursting or the splitting failure. But at this point of time, think it this one, that divergent compressive stress field is a problem and can cause bursting or splitting type failure. But in reality, many times you can have this divergent stress field, so you have to deal with them rather than assuming that it is prismatic. Okay. Now these figures are there in the standard as well from 7.2.1. Now the design strength of a compressed strut is given by the CU, that's the ultimate compressive load, is given by this design strength is given, not the load, the design strength is given by this. Can you see there are two components here? The first one, or the first term, represents the strength of the concrete, and the second term represents the strength of the steel, which is if provided to carry the compression. So if you look at the first term, you know all these terms, right? Because we know F prime C AC, which is basically the compressive force. F prime C is not F prime C, we'll add the 0.9 also. So that means we have considered the 0.9 times F prime C, which is basically your compressive strength. Now F prime C is the characteristic compressive strength of concrete, which you are already familiar with. Then AC is the cross-sectional area calculated using the smaller depth C. The smaller depth at the end of the strut, that is the cross-sectional area of the face at the critical node. Because if you have different cross-sectional area, different nodes, then obviously we need to go for the smallest area, isn't it? So design based on design the strut based on the smallest cross-sectional area at the face of the critical node. So that's your 0.9 times F prime C times AC. And then you have this beta S, which is a factor, which is called the strut efficiency factor. We'll come into that in a minute. And then you have the phi ST, which is a strength reduction factor, which is 0.65. Now, remember one thing, the capacity reduction factor, which we have used for other models, that means designing concrete structure using the other approach they all use table 2.2.3. I think it's table 2.2. Let me check this one. So it is your 2.2.2. Sorry, not 2.2.3. It is 2.2.2. And when you look at the strut and type modeling, we'll be using table 2.2.4. Very important to check these things. This is the new thing. New means if you look at the earlier standard, this factor was 0.6. So there's a slightly improved capacity factor. That means the members in reality can have a more capacity. So phi ST, the strength reduction factor for compression. Remember, this is for compression we are talking about, because strut carries compression. So the capacity or the strength reduction factor is 0.65. Okay. So look at table 2.2.4. And remember, this is only related to the strut and tie method of analysis. Now, the depth of the strut is measured normal to the axis of the strut. We'll look into the figure. It is understood. AST, the cross-sectional area of the reinforcement that is placed parallel to the axis of the strut and properly anchored. That means if you have the strut like this, your reinforcements will also be like this. Okay. And your depth of the strut will be measured. So this is your, yeah, what is measured normal to the axis of the strut. Imagine this is your axis, centroidal axis. Drawing may not be the scale, but imagine that's an axis. So this is your strut depth, say D. D is whatever you call it. And what is the width of the strut? The width of the strut is equal to the width of the member, isn't it? Because the whole member is active. Now, as per clause 7.2.2, for prismatic strut, the strut efficiency factor beta S is 1. Okay, that's fine. But if you have an unconfined compressive field, like fan or bottle-shaped compression field, we can use this expression to calculate the beta S. What it tells you is this. If you have a prismatic one, that means prismatic compression field, then your beta S is 1. That means you get the full efficiency. But as your compression field becomes more and more divergent, that beta S will reduce. And you can see 0.3 is the lowest value. That means you can see that there will be a 70% reduction of the capacity maximum if there is a divergent stress field. And depending on the orientation of the member, or the orientation of the strut, that's your theta, we can calculate the beta S. Now here in this figure, this is your theta. For example, if there's a tie there, this is your theta. That's the orientation of the strut. Okay. So what we have understood is, yes, unconfined compressive field is a problem. And if that happens, then we can deal with that just by using this strut efficiency factor. Okay. Now, to prevent the bursting forces of bottle-shaped struts, bursting reinforcement needs to be provided as per clause 7.2.4, satisfying both the serviceability and strength requirements explored. This is very important. We'll talk about that later in this module, but this is very important to note. That's what I was talking about before. If the compressive field suddenly becomes divergent, there is not slow, divergence. It is like sudden. Then what happens is you actually get what is called splitting type of failure or bursting type of failures. As a result, what one can do is one needs to provide additional reinforcement to take care of the splitting or bursting phenomenon. So this is an example of how to provide the bursting reinforcement. Now, what happens is, if you look at the axis of this is your axis of the strut and this is your strut. Now, we have provided this bursting reinforcement in terms of two orthogonal sets of orthogonal reinforcements, one in the horizontal direction and that is in the vertical direction. And that's the way people tend to provide. Instead of providing along the strut or any other direction, the general practice is provide in two orthogonal directions. But yes, of course, one can provide in one direction and then it can cater for, that's possible. But usually that is the standard practice. Okay, and you can see these two ones, the AS1 makes an angle of gamma 1 with the axis of the strut, and the AS2 makes an angle gamma 2 with the angle of the strut. Okay. Now, the ties or the tensile stress fields are in the form of, now we are looking into tie. We have seen what is the design strength of a compressive member. That means a strut. Now let's look into the tie. Tie is usually provided what? We know that steel reinforcement. That's class N. Standard clearly recommends use class N type reinforcement. That means the normal ductility, normal ductile reinforcement, or pre-stressing tendons, or both. Okay, both of them. The design strength of a tie, clause 7.3.2, is given by this. Can you see that? First term is due to the reinforcement. Second term is due to the pre-stressing tendon. Very clear. Now, in this case, we are not going to any pre-stressing tendon, so I am not explaining this term. But yes, if you use pre-stressing tendon like pre-stressed concrete members, then yes, you include this term, and then you have to check those things. So, for example, sigma py is the yield strength of the tendons, and P stands for the tendons. If you look at the standard talks about these things, that this is your tie, okay? And the value of phi st, in this case, from table 2.2.4 is 0.85. Again, this is an increase from the previous standard. Earlier it was 0.8, now the strength reduction factor is 0.85. Remember, this is for tension because we are talking about tie here. Okay, so this is very simple expression. Strength of the tie, you see, this is an axially loaded member, isn't it? We have seen in case of compression. You see, there is no complexity because there is no bending involvement. Compression, concrete member is in compression. So we know how to calculate the strength. Here also we have a tie. We provide the reinforcement. AST is the area of the steel provided times the yield strength of the steel times phi st. That gives the design strength. So that way you see that the approach is quite simple. Important to note the arrangement. As per clause 7.3.1, the reinforcement and or tendons need to be uniformly distributed, very important, across the nodal regions at each end of the tie to ensure what? To ensure, I will tell you to think of that, to ensure that the resultant force, for example, okay, let's look into that, then it will be clearer. So what we are saying is we are applying some force here, right? Say this tensile force. Now, this has to be carried by the reinforcement which is provided inside this tie. So what will happen, what we are saying here is this: distribute the reinforcement required into equally, that means uniformly distributed across the cross section. So that way what happens, the centroid of that applied force will be equal to the the resultant tensile force will be applied to the centroid of the cross section, and the applied force is also acting to the centroid of the cross section. That means there is no additional moment generated. So this is very important. So that's what we are talking about, the arrangement. And you can see we can provide multiple layers because sometimes the depth can be higher. You can provide multiple layers, and you can see the whole member is in tension in this case. Next, we'll look at the anchorage. The reinforcement should be properly anchored at its ends as per clause 7.3.3. That means, if you recall from the what we have studied in the detailing, same thing. I'll mention the standard clause here. It says the reinforcement or tendon shall be extended beyond the node to achieve the design strength of the tie at the node and be anchored in accordance with clause 13.1. That's your detailing clause. At least 50% of the development length shall extend beyond the nodal zone. And because that is not possible, what I mentioned here, this 50% one, what happens is many times you have to provide what is called the mechanical zone, a mechanical type of anchorage. So you provide a plate or something and then weld the reinforcement here. Remember, we were talking about the figure before. So you provide a plate. So that's a mechanical system. Sometimes we can also weld it to another bars if possible, but otherwise this is people use. So you provide a plate at the end of the beam and then weld the reinforcement. So that will provide the anchorage. But it is very important that you provide the anchorage here, especially in this case, because you will see that the magnitude of load is extremely high. So you have to provide proper anchorage, and this is very important. At least 50% of the development length shall extend beyond the nodal zone. Next, we'll look into the nodal zones. The nodes can be divided into three types. You can see I've said three, depending on the arrangement of the struts and ties connected to it. So what are these three types? Triple C, the nodal zone bounded only by struts. That's why CCC. So there are three members connected to a node, but all are the compression members. That means they are all struts. CCT, the nodal zone is bounded by two or more struts with a single tie connected to. That's why the T is. And CTT, the nodal zone has two or more ties passing through the node. Okay. And what happens is, why you have classified this way? Because the nodal efficiency will change and in fact will reduce when you have more and more tension members associated, or not associated, connected to the node. So why is it so? Why do you think? Because more and more tension member associated to a node means you are subjected, the nodes are subjected to tremendous tensile forces. And you can think of that because concrete is weak in tension, it is always a problem, isn't it? So that's why when more and more tension members are connected, that means the ties are connected to the nodes, the node efficiency will be reduced. This is a very important figure, geometry of a typical CCT nodes. Now the strut angle is given by this one, yeah, theta. Some say this only not, notation is not clear, though it's basically looks as the new. So it's the strut, that's the strut angle. That means the angle which the axis of the strut makes with the tie. And then what happens? You can see the strut depth, which is this one, can be calculated as LB sine theta plus DA cos theta. What is LB? LB is the size of the bearing plate. That's your length of the bearing plate. And you can see DA. What is DA? DA is the anchorage or the depth of the tie. And that means the strut depth can be calculated from geometry like this. This is calculated from geometry. Can I encourage all the people to please derive this equation? Derive this equation is very important. But remember, this is only possible, or this is only valid for a hydrostatic node. Hydrostatic node means that all the forces are subjected to normal forces. There are no shear forces. That's why we call these nodes as the hydrostatic node. Come into that node classification in a minute, but imagine that, okay, so in this particular case, this is your node and you have this tie and then you have this strut and then you have the bearing plate. So this is basically the members which are connected to the node. LA is the anchorage length. You can see section for development of tie reinforcement. It is very important, yeah? And that's your extended nodal zone. So that's a typical CCT node. So there are two compression members connected because bearing is also under compression bearing plate. And there is one tension member, which is this one. So this is a geometry of a typical CCT node. I encourage all of you to derive this expression DS by LB as this. And then you learn why for a hydrostatic node it is much easier to design. And the important thing, I'll tell you this, that means because you can calculate the strut depth on with respect to LB, DA, and theta. Once your orientation, say the orientation we know, but once your LB and D is finalized, your strut depth will not change. That means if the strut fails in compression, what you have to do? You have to redesign the node. This is very important. Remember, if any member fails, for example, the strut can fail. If the strut fails, then you have to redesign the node. Bearing plate, probably first you design, then you make it safe, it's fine. Tie, you are providing reinforcement, but strut can be the problem at many times. And then what you have to do, simply redesign the strut. So I'll just use the word redesign. Redesign the node. And redesign essentially means this will be changed, this will be changed. Because the whole dimension of the node will change. The node might look like the bigger node, so that you get a greater depth here, isn't it? That's what the purpose is. Yeah. So a bearing plate also has now become a larger bearing plate. That's okay, because we want to make the joint safe, and this is your depth of the tie. Okay. So your LB, and this becomes your DA. All right. Now we are looking at these different nodal zones. We have already looked at the hydrostatic node. All the members are at right angles to the node face. Very important. Hence, the node is free from shear stresses, only subjected to normal stresses. So if you go to this one, all the members are actually perpendicular. For example, the axis of the strut is perpendicular to the nodal face, and the stress is perpendicular to this nodal face. Bearing plate is perpendicular to this nodal face. Yep. So that's why the node is free from shear stresses, only subjected to normal stresses. On the other hand, if you look at non-hydrostatic node, if any one or more members are connected to the node other than the right angle, then the node is called non-hydrostatic. Load calculations can be complex. Why complex? Because in this case, the members will, node will be subjected to shear forces apart from the normal forces. Yeah. So in addition to the normal forces, they will be subjected to shear forces. And that's why the load calculations will be complex. And that is why designing a non-hydrostatic node is always a challenge. Excuse me. Now, how to design the nodal zones? As per clause 7.4.2, the design strength of a node without any confinement will be such that the maximum principal compressive strength, which is a maximum 1, on any nodal face sigma c will be given by this, where the phi st is the strength reduction factor from table 2.2.4, beta n, this is the thing I was talking about before. Beta n, you can see this is called one could actually view it as the nodal efficiency factor. Remember, this n stands for the node here. So beta n is a factor, then 0.9 times F prime C is the compressive strength of the concrete, which is understood. Phi st is the strength reduction factor, that is also understood. And we are now saying the value of beta n, you see, for CCC, that means if all the compressive members are connected to the node, then there is no reduction in capacity of the node. That is beta n is 1.0. But if you have CCT, that means there is one tie connected to the node, you get beta n equals 0.8. On the other hand, if you have two tension members, that means two ties are connected, then you get beta n equals 0.6. So you can see the nodal efficiency, you can think in that way. Nodal efficiency is getting reduced when you have more and more tensile members connected to it, simply because that we are trying to pull the node apart, which is the problem, isn't it? Because it is concrete. So concrete is very weak in tension. So if you have more and more ties connected to a node, it is always a problem. And remember, this node, which we have shown before, is an hypothetical, isn't it? Hypothetical in that sense that is also basically a concrete, isn't it? It's part of the concrete member.